Okay, welcome everyone. Good afternoon. Because this is a shorter session, let's go ahead and kick things off right away. So welcome to the SAS Via Transition Lunch and Learn session. To view previous training sessions and to learn more information about upcoming events, you can click those two links. Laura's going to go ahead and drop those in the chat to share with you as well. And then just a quick note as we kick things off today. Starting next week, all lunch and learn sessions and office hour calls will be distributed. The invites will start being sent through our distribution list rather than a Zoom registration. So they will no longer require that Zoom registration because we're not going to be capping the number of people who can join. So if you want to attend, you can simply click like you would any other call. And if you don't want to, you can go ahead and remove it from your calendar. And then the only other thing, we are going to be capping our interactive sessions still. They're still going to have a registration. Those will be capped at 50 just because of the nature of the type of meeting it is and how interactive it is. It would be bogged down with too many participants. So with that, let's go ahead and move over to a couple other administrative items before we hand things over to Tim today. This meeting is being recorded. Please stay muted to minimize interruptions during our call today. Because this is a short session, it will not feature a Q&A session. So please use the Zoom survey at the end of our session today to ask any questions at the end of the lunch and learn that still may be lingering or you want answered. And then all meeting materials will be made available in the CCSQ DNA portal following the conclusion of the session. Just a reminder, please always give us a few days to turn those materials around so we have time to make them compliant and 508 accessible. Okay, so with that, I'm going to go ahead and stop sharing my screen and pass things over to Tim.
Awesome. Thank you, Julia, and thank you all for attending. My name is Tim. I am a senior data scientist here on the user services team. And today we are going to talk about distributed computing in our Databricks environment and what on earth that means. So I'll begin sharing my screen. This screen. Okay. So as I said, the title for today is a little bit of a mouthful. It is Distributed Computing with PySpark Functions, because I'm cramming a lot of little different topics into here. So we are all using Spark, and if you're using Python, we're using PySpark. PySpark is a powerful data analytic and processing tool, but because it is so powerful, it is really hard to use it proficiently. Today, we're going to discuss some of the common pitfalls when doing distributed computing, and we're going to talk about a very specific submodule of PySpark, pyspark.sql.functions, which is going to really help you out along the way. Maybe you've already used it and you've seen it before. I'm going to put it under a little bit of a magnifying glass. So our objectives today are, we're going to understand the difference between distributed computing and the opposite, which I'll call in-memory computing or single-threaded computing or anything similar to that. We're going to realize which calculations you are doing that are causing data to pass from node to worker. And the reason we're going to talk about that is because that will slow your calculations down. And even worse, node to node calculations. That'll slow it down even more. And then we are going to browse pyspark.sql.functions and know when to use it. And spoiler alert, it's going to be all the time. Okay, so what are these two terms? So when working with Databricks, you have two options: working in memory or working distributed. Behind the scenes, the cluster that your code is actually running on is an AWS Elastic MapReduce cluster, which isn't just one computer, it is many computers. The EMR, as we call it, cluster, is made up of one main node, so one centralized CPU that you actually give commands to, and then several worker nodes. These worker nodes are going to be sort of directed and orchestrated by this main node. So what does it mean to work in memory is what I'm going to call it. Here, memory basically means RAM. So working in memory means that the entirety of your data will be read in and is going to be actively used by the main node. You're only using one CPU here. The worker nodes aren't used at all. This might seem a little bit complicated, but this is actually the default behavior when you're working on your own computer. So if you're ever doing anything outside of Databricks, you're working in memory. Right now you're on Zoom. Zoom is running in memory. One computer, that's all there is to it. So it's just a more complicated way of thinking about what you're already used to. Now contrast that with distributed computing, which is what we're going to do a lot of our sort of data analysis on here. Are we going to have access to this notebook after this session? You have access to it now, and you're free to clone it right now too. So if you go to File and Clone, you can save your own personal copy of this notebook. But no, this notebook won't be deleted later or anything. I don't think so. Anyway, distributed computing is the tool of choice for working with large data sets. Instead of reading your data into memory, it is distributed across all of your many worker nodes. When you need to do a calculation, the main node orchestrates the worker nodes. Each worker node does a partial calculation and then returns that partial calculation back to the main node, which then aggregates this information into your result. This sounds really complicated, but you don't need to touch this. It's all being done behind the scenes by Spark, by Databricks for you. So I know that's a lot of words on a screen. You can't see, but I'm like waving my hands here. So I have an analogy. I stole this analogy. This analogy is from the creators of Databricks itself. And here's how distributed computing works with candy. So let's say you have a 100-pound bag of M&Ms. And you want to tally up how many of each color you have. So how many red M&Ms, how many yellow M&Ms, and so on. To do this yourself, this would take hours. This would be in-memory computing. You are one person doing the calculation. It's going to take all day, right? So instead, what you do is you call up 100 friends. Each friend shows up, they take a handful of M&Ms, and they do the tallying for you. Then they record their results on a piece of paper and hand it in to you. This is enough information for you to take their results and gather the final calculation that you need. This is what distributed computing does. You, the main node, distribute instructions to all of the worker nodes, and the worker nodes each do a partial calculation and bring it back to you. This way, we don't need to count up all the M&Ms ourselves. We distribute it across 100 worker nodes. Which then brings up some food for thought here. Was 100 the right number of friends? I think we can agree that 2 would have been too few, but 1,000 might have been too many, right? It just would have taken a lot of time, a lot of overhead to like call up everybody. They all show up, then they all grab a smaller amount of M&Ms and they all send their paper in, and this is a lot for you to do. So 1,000 might have been too many. 2 is definitely too few. What's the right number? So luckily for us, we don't care. Behind the scenes, Databricks actually has a new tool that's going to kind of handle this balancing for you. But in the olden days, this used to be something that you kind of needed to guess and check yourself. But there's rarely a need to adjust these numbers today, although you can. All right, so what does this look like in actual code? And I ran this to make sure I was connected to the cluster ahead of time. Why is it highlighted? Anyway. So by default, anytime you use PySpark, everything is going to be read in as a Spark data frame. So here I'm using the spark.sql command, just use some SQL syntax to read in a PySpark data frame. So I'm just reading in some zip code data. And when you look at the type of this object, and if you're unfamiliar, the Python function type just says, what kind of object is this? So the type of dfSpark is a PySpark SQL data frame. You can look at it if you want, right? We use display to view a PySpark data frame. And here's the first 5 rows, just some zip code data. Now, this data is distributed. I think there's several thousand rows in this data set, and I don't know how many worker nodes I have running right now, but the data is distributed across these worker nodes. And when I say display, it says, okay, Tim, we're going to send some data back for you to display to the screen. So that's it's, we don't think about displaying as a distributed calculation, but technically it is. All right. So how do we work in memory? First, before I even show you how to do it, I want to say you probably don't ever want to do what I'm about to do on the screen here. So technically, you can always cast a Spark data frame back as a pandas data frame. Pandas, if you've never had the privilege of using it before, Pandas is kind of the go-to data science library for working in memory on your own computer. So if you've done like a data science tutorial or you've done previous data science work in Python in the past, you're probably using Pandas. And I know a lot of people are used to using Pandas. If you are a previous Pandas user and you're finding PySpark syntax to be really awkward, there actually is a API inside PySpark to use all of the pandas syntax that you're used to. And there's actually a lot of tricks in there that make a lot of really complicated things like transposing a lot easier. But I'm not going to be going into that today. You can cast PySpark data frames down into pandas. And there's a toPandas method for this. And if I look at the type of it, it is indeed a pandas data frame. Now, why should you never really do this? Because this operation is forcing all of your data onto the driver node, the main node. This is oftentimes impossible, right? The whole reason we're using PySpark is to work with super large data sets. If you have, 100 million rows of data distributed across all of your worker nodes, and you try to cast it as a pandas data frame, Pandas can only work in memory. So it's going to try to take all of that data and shove it onto one computer, which is probably impossible. For most data sets that we work with here, it is just simply too big. You can't have 100 million rows on one computer. So your calculation, your cell execution is going to take a really long time, and then it's going to break. And then your cluster might shut down and a fire might start somewhere. I don't know. You shouldn't be doing it. You can do it if you know in advance your data frame is small enough and you know what you're doing. But generally, you don't want to be bringing this thing into memory. I happen to know that the zip code tutorial data that we have is super small. It's only a couple thousand rows. I think it's like 10,000 rows. Well, actually, we can find out. So in this next cell, I call it .info, which is a pandas method. There are almost 43,000 rows of this data set, apparently. And down at the bottom here, it even tells you how much memory this table takes in RAM. It is about 4.6 megabytes, which is microscopic. For reference, that's approximately the size of one song. Back in the day when we all used iTunes, one song takes about 4 megabytes. So this is a really small data set. Most data sets we work with, millions and millions of rows, going to be several gigabytes. Can't read that into memory and work with it comfortably. So, when do you want to use each of these? I have some short answers. You want to use pandas when your data are small enough to reasonably fit into memory. How small? Can't really tell you. But as a general rule of thumb, a million is probably too big, although it definitely depends on the number of columns you're working with. And you would only want to do this if you're already very familiar working with pandas. If you don't know what I'm talking about, every time I say the word pandas, you think I'm talking about, the bear, the animal. Don't worry about it. Just never use it. You want to use PySpark when your data are too large to fit into memory and need to take advantage of distributed computing. So that's like 99% of the time for the data that we're working with. Or an even shorter answer is just always use PySpark, right? This is important. This is kind of what we're built to be working with by using the Databricks ecosystem. Databricks is meant to be working with distributed systems here. And it's important because a lot of the data types we're going to be favoring in our systems, specifically Parquet and Delta tables, only work with PySpark. You cannot read a Delta table or a Parquet table using pandas. You just cannot do it. So regardless of the size of your data set, oftentimes you just kind of want to be using PySpark anyway. So just always use PySpark. It's worth learning. It's the tool of the future, and it's really, really powerful. Okay, so you might have been given some false promises when moving over to PySpark, which is it's going to be fast. And maybe after working with PySpark, you realize it's not fast, it's actually slow. Why were you promised speed? And it's because it's only technically very fast. So technically, Spark doesn't actually speed up any individual calculations. These calculations are only going to run as fast as the computers can handle them, after all. But it spreads out those calculations across many worker nodes. So for example, nobody's counting M&Ms faster than anybody else, but when you distribute those M&Ms across 100 people, the overall task will take less time, and hence it appears to be going faster. But there's a little bit of overhead here. The act of both distributing data and instructions to the worker nodes and then collecting those results back and aggregating those results, that also takes time. That's a little bit of overhead. So if your data isn't very large, this overhead might actually slow down your calculation compared to working with pandas. Now, I have an example in a minute. The slowdown isn't really that bad or anything, but it takes more than a split second. And when things take like, 1 Mississippi, you tend to notice that over time. So for large data sets, this process is much faster than working with pandas because it would be impossible otherwise. And here I've made a little bit of a table kind of explaining what I'm talking about here. So if you have really small data, everything you do in pandas is going to be lickety split. A split second, you blink and you miss it. But if you have small data and you're working with PySpark, it's still fast, but you'll notice the delay. It'll be like a second or two. And you're like, my data set's only 100 rows. Why is it taking 2 whole seconds to do a row count or something like that? That's because it's still fast, but there's that overhead we were just talking about. Now, if you have big data, the difference becomes really clear. You just can't do it in pandas, right? After a certain point, the calculation just becomes impossible. But with PySpark, it becomes possible, and the time it takes to carry out that task is a function of exactly what you're doing, the size of the data set, and the computational power of the cluster you're running on. But at least it's possible, right? Your calculation might take an hour, but it would take like 80 years to do in pandas. All right, cool. How do we access these calculations? Well, if you're used to working with pandas or any in-memory libraries of working with data frames, you might reach for npmean or calling .mean on a pandas data frame. If you're used to those things, you might notice that they don't work as well as they should if they work at all. And it's because those calculations are not distributed. They're in memory. So again, you're running a risk here of pulling all of your data into memory and then crashing your cluster if you're using these functions by accident. The distributed version of these functions exists in pyspark.sql.functions. And you can import functions out of here one by one, but it is often done to abbreviate it just as capital F. And because pyspark.sql.functions is kind of a mouthful, I'm just going to call it capital F sometimes. So let's do it. Import pyspark.sql.functions as F. And I'm going to do a quick little calculation on the zip code data. So the data that I had read in is a list of, I think, all of the zip codes in the United States. So I'm going to do a filter on the state to be Maryland. And you'll see here I'm using f.call. I'll talk more about this one specifically, but this is how I address a whole column of the table by using fcall. Then I'm going to group by county. And then I'm going to sum up the population. And I'm using f.sum. And then I'm going to make a new column called is large, and it's just going to say if the population of that county is above 100,000, yes, the county's large. Otherwise, no, just an arbitrary number I picked. So there's f.when. This is like an if-else in PySpark. So if you're used to, Excel, this is if. If you're used to pandas, it's np-where, right? It's an if-else, right? So when it's above 100,000, yes, otherwise, no. And of course, I have to use fcall again because I'm addressing a column by name. And then I'm going to sort by county. And I run this cell, and it is super fast, less than 1 second to run here. But nothing has happened. Remember, PySpark is lazy, which means what you do is you send it instructions, and it doesn't actually carry out those instructions until you absolutely need it. So when I run this cell, no math is being done. No calculations are being done on the nodes. It's just storing these instructions. And if you're brave enough, you can see these instructions. So you can do a .explain on the query here. So it's difficult to read, but the back end of Databricks uses an engine called Photon, which is basically a super fast calculation engine, and it creates an execution plan. This execution plan apparently has 15 steps, and you can read some of them. Some of them are pretty hard to understand, but sort, right? We're sorting the data towards the end there. Shuffle, group aggregating, that's the group by, I think. Proton shuffle map, I think that's I don't know. Um, you can analyze this if you want, but these are the instructions if you really wanted them. Okay, but still, these instructions have yet to be carried out. How do we force it to do it? Because it's lazy, it doesn't do it until it absolutely needs to. So I'm going to call a display on this table. And by saying like, hey, okay, I actually want to see it, Databricks will be like, okay, we'll do the calculation now because you really want to see the answer. So let's display it. Now our calculation did not take very long. It took a third of a second. And here are the results, kind of as I promised. So here are some large counties, some small counties, but it took a third of a second. So that's not so bad, right? Let's do the equivalent calculation in pandas. So I'm taking the pandas data frame that we brought into memory earlier and doing the exact same calculation. So to filter in pandas, you use square brackets like this. I'm doing a group by, creating the total population again, then I'm sorting by county. Pandas doesn't have a really good way of doing like a with column in pandas, so I have to do it on a new line like this. And I'm just going to print it to the screen. And up at the top here, I have a macro %% time. This is a special Databricks command that says time the whole cell. I want to know how long it takes. I didn't have to do it before because when you do distributed stuff, the time shows up automatically. But for non-distributed stuff, you do have to time it yourself. Okay. So we get the same results because it's the same data frame with the same instructions. But look how long it took. 17.7 milliseconds. Compare that with a third of a second. That is orders of magnitude faster because it doesn't have that overhead of doing distributed calculations. Again, for a table this small, it's not really noticeable. Like a third of a second is still less than 1 second, which is really hard to complain about. But when it comes to a ratio of not doing it that way, it is actually a little bit slower. But again, this was in memory. Yes, this was fast, but you can't do it with 100 million rows, right? So this is maybe a little bit of a pipe dream here. Okay, so I have some FAQs here. What else is in F? So I have the documentation here, and there is a lot in here. And you can look at sort of like the table of contents on the side. So maybe I could zoom a little bit. So they have here what they call normal functions, which are basically like helper functions. Fcall is in here. I'll talk about that one in more detail. But if you look, there's some math functions, some trig, square root, things like that. Datetime functions. Who doesn't have fun with datetime stuff in PySpark? I hate it. Anyway, collection functions, so aggregating things. Actually, I don't recognize a lot of these. Partition and window functions. So if you want to do window stuff, that's all here. Aggregate functions, this is what I meant for aggregating like sums and things like that. String functions, Boolean functions, sort functions, and anything that you could want to be done distributed rather than in memory, it's all in here in F. So all of the normal calculations that hypothetically would take a long time are sped up in here. All right, so what is f.call? Because we use it a lot and we have to use it a lot. This is a frequently used function that allows you to address a single column without writing code that is too long or confusing. So in calculations, you can write fcall of state for the state column rather than the data frame bracket state or df.state. And in certain places in Spark, those options won't work anyway. So f.call is just how you say, I mean the column, right? Like I mean the column called state. Okay. Let's say you did all of my advice for, having really fast calculations and something took a really long time and it turns out it's f.median. f.median takes a really long time. Why is that the case? That's because there are some calculations that are not really easy to distribute across your worker nodes. And median is a really cliche example of that. So distributed computing works best when the main node sends out instructions to the worker nodes, and the worker nodes can just send the results right back. But there are lots of very common operations where the worker nodes need to talk to each other. And this is sometimes called a wide transformation, because, or rather a shuffle transformation, because the data needs to be shuffled around the worker nodes. And this is really, really slow. So for example, the median, how do you know what is the center of the data after it has been sorted unless the worker nodes can actually talk to each other? So this is what we call a shuffle transformation or a wide transformation, because the nodes need to talk to each other. And when you think about it that way, you could probably think about some other shuffle transformations, such as sorting your data, right? How do you sort the data unless the data can talk to each other? So these shuffle or wide transformations should be minimized. You should not be doing them unless you absolutely have to. And in the case of sorting, you should really only sort the data after it has been filtered or aggregated. So you're only sorting a couple rows as opposed to a couple million rows. So just be mindful that, not every calculation is as fast as advertised. Okay. So thanks for hanging out with me. Oh, sorry, I do have some additional notes before I conclude here. So some other really quick notes. So you're really entertained by what I said, but you're not a Python user, you're an R user. What about you? Well, good news is a lot of what I talked about today is handled behind the scenes in the R language. And that's because Sparkly R, what it seeks to do is it seeks to overwrite the tidyverse with Sparkly R functions. And because of the way the R language works, as opposed to Python, in R you can actually overload a function. So what I mean by that is when you call the mean function might do something totally different depending on what you're taking the mean of. So if you take the mean of a in-memory data frame and you take the mean of a distributed data frame, those are two different mean functions that will be run, and Sparkly R will handle that automatically. So you don't have to worry about it in R. That is until you do have to worry about it, and it's really hard to pick apart what you just did. But in general, you don't have to worry about this stuff in R. It's, Sparkly R is really good, and Databricks is really good. So a lot of it's done behind the scenes for you. Okay, so that's my note on R. Another note is F doesn't have everything, and you might find that you need to do some kind of calculation that is not included in capital F. First step is to say, okay, how can I take a combination of the things that are in capital F to do what I want to do? You should try really, really, really hard to use functions provided in F to do what you need to do. But in case that isn't possible, you have to do stuff in memory, which is in a lot of ways a nightmare situation. An alternative is to use a UDF, a user-defined function. Technically, there is a way to create a function that is non-distributed and then distribute that non-distributed function to each of the nodes and have it run that way. That is called a UDF. You can look up how to do them. They're kind of cool, I guess, if you need them. But I don't want to talk about them too much because you probably can't do them in our setup. So unfortunately, UDFs require a permission structure that you very likely don't have. I think I don't even have the permission structure to carry out a UDF. So too bad, so sad. You really should be trying to figure out how to do this with capital F. I'm sorry. There's got to be a way to do everything. But UDFs are probably not allowed. All right. Now, thank you for joining. Some closing notes. What have we done here? We learned the difference between doing calculations in memory and via distributed calculations. Long story short here is stay inside Spark if you can. It's really just kind of the way we're meant to be doing things. You're not really supposed to stray too far out of Spark, PySpark, Sparkly R, whatever it is. And you should always be mindful when you carry out commands that collect data onto the driver node. I'm very often on call for our user services help desk, and a lot of the issues that we get are code and clusters that break down because the user doesn't understand that one of the many calculations they're doing brought all of their data onto the main node. And our answer is don't use that function, use this function because it's distributed, and wouldn't you know it, the code runs in less than 1 second. So just be mindful of what we do is called collecting the data onto the main node. And
Hey,
you
Tim,
can
are you
find function.
okay? Oh, sorry. Go ahead.
I'm done. The last bullet is just look into the pyspark.sql functions for whatever you need. Oh, I did go after 1 o'clock. I'm so sorry.
That's okay. We do have a quick survey to administer, if anyone would mind holding on. And then as soon as you wrap up, you can drop. Thank you so much to Tim, and thank you to all of our attendees today. As I said, the survey will be administered here. Let me actually launch that while I'm closing up. And then just please make sure you're giving us feedback so we can continue to improve and make sure these sessions continue to be beneficial. And there is that spot for you to ask any questions that you may have. And then Tim, I don't know if you're seeing the chat, but lots of good feedback there. So thank you so much to everyone. And as I said, once you submit your survey, please feel free to drop. Thank you, everyone.
Awesome. Thank you, everybody, for attending. Thank you, Julia, for hosting. And I apologize for going long, I think, again. Sorry. Bye, everyone.